The space has been a dream destination for humanity for millennia, said Elon Musk. Nebulas, galaxies, we are all condemned to contemplate this distant paradise. But in the void of this space, we still have fairly close neighbors in our solar system. Because humans have always had the desire to explore, to seek their origins, we have explored the neighboring planet several times. That's what motivates us to explore Venus and study a way to perform an atmospheric reentry. So, with my colleagues Nitish Narasimhan and Marianne Denis STANOIU, we are going to present you our own way to create and perform a reentry on the atmosphere of Venus. We have to know that few missions have already been conducted on Venus before. For example, there was the Venera 12 missions, a Soviet space probe launched on September 14 of 1978, and this mission was performed in order to study the atmosphere and surface of the planet Venus as part of the Venera program. This is this mission that inspired us to create our own module, and you will see this later. So, with my colleague, our atmospheric reentry presentation will proceed as follows. First, we will study the journey of our module at the arrival at the entry of Venus atmosphere, and that is where we will present our module and what we have chosen to bring in. So, initially, we have a module that will remain in orbit, and then a module that will perform the descent. Next, we will study the optimal descent path to counter disturbance towards the module in the atmosphere. Then, after this long descent, we will present the shape and the characteristic of our landing module. In order to perform our descent onto the Venus atmosphere, we should first take in consideration the interplanetary travel. So we check on NASA websites for data about the interplanetary travel time and the start date, and we found that it will take approximately 130 days if we launch our module from Earth on the 20 June of 2026. Considering the height, but also the previous mission's entry parking orbit altitude, we chose to perform our reentry at an altitude of 250 kilometers with a reentry velocity of 12.2 kilometers per second. In order to perform our reentry, we will need to bring our module to the top of the atmosphere. So, how will we proceed? At the top of the atmosphere, the module will be dismantled in two parts. One part will be kept to ensure the communication with Earth, and the other part will land on Venus. The objective of this orbital module is obviously to keep a communication with the Earth, so this go by storing and relaying data from the atmosphere and ground probes to Earth, but also to carry on observations on the Venusian atmosphere. And for these observations, we think about putting an infrared telescope, but also an optical telescope, and also because the atmosphere of Venus is really perturbed by clouds, to put a Doppler radar for cloud analysis. When an object enters the atmosphere of a planet, it is submitted to extreme conditions, including a significant increase of temperature and pressure. So, these conditions can lead to physical and chemical change in the object, especially when it comes to molecular-based materials such as comets, meteorites, or spacecraft. So, it's essential to consider the molecular regime during atmospheric entry for several reasons. We were able to simulate the mean free path, meaning the transition between different molecular regimes of our module throughout the atmosphere of Venus. The molecular regime of an atmosphere depends on the Newton number. It's a number characterizing the flow of a fluid. Up to 74 kilometers of altitude, our module will be in the free molecular regime. From 49 to 74 kilometers of altitude, we are in the transition regime. From 43 to 49, we are in the slip flow regime. And from 0 to 43 kilometers of altitude, we are in the continuum regime. By considering the molecular regime during atmospheric reentry, we can assess the interaction between the object and the atmosphere, then predict the forces, temperatures, and chemical reactions that will occur, and thus design more resilient materials and structures capable of withstanding these extreme conditions.
So in this slide, we are going to talk briefly about the simulation we have done about our module re-entering the atmosphere and what can we expect. Well, first of all, we can expect very high deceleration loads up to 80 Gs and very high temperature increases. Um, well, why is that? Well, because we need to lose a lot of kinetic energy, more exactly 40 gigajoules. And we are going to travel mostly in hypersonic regime. Um, and other obstacles we can expect, well, we have already mentioned the thermal loading, which can melt the skin of our module. And we also need to consider aerodynamic forces and vibrations. In order to tackle the issues exposed previously, mainly the thermal loadings and the vibrations and the acceleration loadings, we have decided to create a hemispherical module which is going to have a maximum diameter of 6 meters and a surface reference area of 28.27 meters. The shape is going to be conical with a very wide angle at the bottom and then hemispherical. Uh, the thickness of the material of the thermal shield is going to be 50 millimeters, and the material is going to be TZMK10, a silicon dioxide based material developed in the Soviet Union and used on many of their space programs. As you can see, this is a representation of our module. It is going to be split in 4 key parts, which are going to be detached from the modules in sequence. First, the first parachute is going to be deployed at an altitude of 60 kilometers, and after descending for 5 kilometers, it's going to break away together with the balloon, which represents the atmospheric analysis module. Then we have a second parachute, which is going to further slow down our landing module. Then we have the systems bay, which is going to stay with us until we reach the planet. And then we have the ablative thermal protection shield. Now we are going to talk a little bit about the first part of our landing module, mainly the atmospheric module. This is an aerostat or a balloon with a canopy attached which contains the measurement instruments. The balloon is expected to be deployed at 55 kilometers of altitude and it will remain stationary at 47 kilometers. The expected challenges have been identified in the previous slides detailing the atmospheric model, and we have found out that at this altitude we have conditions roughly similar with mean sea level conditions, mainly 1 atmosphere and 300 Kelvin temperature. The expected mass of the module is going to be 20 kilograms, and it also needs to have some protection because the layer of the atmosphere is covered in sulfuric acid clouds. A bit more about the atmospheric module and its schematic. As you can see, it is a balloon with a canopy attached. On the canopy, we are going to have a photovoltaic surface on the top. We actually wish to be able to mount electronic actuators which can uh, elevate this surface and orient it after the sun, but this is mainly a project. Then the important part, we have static pressure ports and dynamic pressure ports, which are going to act like a pitot tube. And we also have a venting port, which will be used to cool down the internal components of our canopy. Furthermore, the static pressure ports are going to be used to collect air and perform chemical analysis on the air samples.
Now for the bottom part of our atmospheric module, we have first a thin radiative panel that will supply the system in electric power in order to keep it enough alimented to make the system of communication and observation work. Then we have the optical captor that will be used for capturing images of Venus. And with the captured images, we put on the module an ISA radar imager that will perform the post-treatment of the image. The main objective of our atmospheric module is for some observation and calculation inside the atmosphere. So as embedded instrumentation, we'll have a pitot probe, an anemometer, a chemical sensor, of course, and also an optical imaging sensors that will be able to catch images in a wavelength between 1 and 100 micrometers, and a radiometer. The chemical sensor will be useful during the descent because the chemical properties of the atmosphere change in function of the molecular flow we are inside. With the pitot probe, we'll be able to measure, to estimate the velocity of the fluid. And because the winds on Venus are really important, the anemometer will be useful to measure them velocities.
A bit about the challenges we are going to face when designing the landing module, which is actually going to touch the surface of Venus. Well, the biggest problem we are going to encounter is the lack of luminosity. This makes it impossible to rely on renewable energy sources, so no solar panels or and anything like this, because they will have no input. As such, we will have to rely only on batteries, which will provide a very short lifetime. And another problem is the high temperature. At 400 degrees Celsius, it is going to melt many alloys that are not made out of steel. As such, we can further expect a decrease in the lifetime. The pressure of 10 bars is always also going to be a problem, and we also need to factor in the acid atmosphere.
We have to be really careful with the choice of the equipment that will be embedded on the landing module. We'll need an adapted landing cushion in order to have a good damping of the shock within the fall. About the batteries, it's hard to choose because of the high temperature on Venus, the lithium-ion seems not adapted, but it's the more effective in terms of runment and longevity. And we'll have a bunch of sensors that will send the information to the orbital module as optical sensors, a chemical sensor, but also a ground probe.